Evening or good afternoon. My name is Haris Kulzar and I'm master student in Tokyo Institute of Technology, and I'm going to present on the topic CNN acceleration for speech classification in edge computing, and CASE is the shorter version of that. First, I will start with the introduction and background. So the application of speech interface is becoming very common in our daily lives, where we use many devices like smartphones or smart speakers to control smart devices at our home, like home assistant robots and smart appliances. But how does the conventional speech recognition system works is that the speech data is sent to the cloud where most of the processing happens, and then that cloud, after performing recognition, sends commands to the smart devices. This has some issues. For example, the first issue is it needs a stable internet connection, and depending upon the connection quality, the latency may be high. And also it poses a privacy concern because we have to send private speech data to the internet. Thirdly, because in our daily life, number of smart devices are been increasing, and cloud computing is not a scalable solution. So we need edge computing resource for these kind of applications. So here is where the edge lies in this scenario. So edge computing is near the application, and this is a compute resource which is based upon local access points instead of global access points. So speaking of edge computing, when we deploy these kind of applications on edge computing, there are certain challenges, and obviously the main challenge is limited computational and energy resources, because edge devices are basically scaled down version of computational clusters on the cloud. So considering this challenge, our work makes following contributions. It explores latest convolution neural network architecture while maintaining state-of-the-art performance for speech classification or speech commands. Efficient sound features extraction leading to good classification with small network size. Also, FPGA accelerator design for CNN network to achieve lower latency. So I will discuss the related work. So in speech classification, there are basically two approaches. First is a recurrent neural network based approach. So from our literature view, which we have done, we have found some approaches which perform speech classification using RNN. But the problem here is that it achieves good performance, but the number of parameters are quite high, which means it requires a large memory, and we don't have enough memory on edge devices. Second approach is a convolution neural network based approach, CNN. So it is efficient in terms of parameters over memory, but performance improves when the network size is significantly large, which means the number of floating point operations for CNN would exponentially increase if we increase the network size. So high floating point operations means higher latency, which again is not a desirable scenario. So our CNN network maintains the performance with smaller number of parameters and flops, and I'm going to explain the details. So first of all, I will introduce the data set which we have used in our case. So basically, we have used Google's speech commands dataset, which are basically set of 10 basic commands, simple ones like yes, no, up, down. And these are in form of audio files, which are 1 second long each. And it is sampled at 16 kilohertz frequency. And we have divided our dataset into two parts as 80% training data and 20% test data. And we have also performed data augmentation to increase the size of training data. So input feature extraction is the important part for speech classification. So in our case, for example, this is the audio signal, which is in time domain. So we take this Mel frequency substral coefficients, which is something like Fourier transform. So it takes a 25 millisecond window in the time domain and converts that into frequency domain. And we take 30 MFCC features, which means we have 13 frequencies for each time bin. And these are the most commonly used features in speech classification. After that, we used some extra features from audio signal, which are delta. Delta means we take the difference of the magnitude from the consecutive frames, because the audio is like a variation of different phonemes. So if we take the difference between connective phonemes, it serves two benefits. Firstly, because it's a difference, it suppresses the white noise. And secondly, it gives an additional information for our signal. And after taking the delta features, we again take the delta of the previously taken delta features, and which are known as double delta. And finally, we take the power of one frame as our 40th feature. So the reason for using these extra features is clear. For example, for the same machine learning network, by using these extra features, the network performance has been improved by 1% without changing any other thing. Next, I will explain more about the network and its comparison with other networks. So this is our network, which we call CaseNet. Case is the short version of CNN acceleration for speech classification on edge devices. So it's basically a convolution network with 3 convolution layers followed by 1 fully connected layer. And we have made 3 variations of our network. The largest one has 3 convolution layers with these number of parameters, and it has 2 to 4,000 parameters. And then we also do experiments with CNN only using 2 convolution layers, just to check how the number of convolution layers affect the performance. And then for the final version, we take 3 convolution layers network and reduce the number of parameters almost by 3 times. And this is how the performance looks like, that we have almost maintained the same performance as very large networks. And this is because of the use of additional information from the audio signal. And in short, our CaseNet 1 lighter version achieves same performance as a standard implementation of CNN in this reference, with 6 times smaller number of parameters. And it also achieved same performance as Res 15, which is a CNN-based model with a 14 times smaller number of floating point operations. Moving forward, I would like to introduce the hardware which we have used. So the device which we have used as edge server device is named as MQ-BOSS, which is a custom-built device, and it is built by this Japanese-based company. And it has a processor which is named as system on chip. System on chip means there are 2 parts. One is programmable hardware, and the second one is a processing system, which is ARM-based processor. And both of these processors are fabricated on the same chip, and we call it system on chip. And both of these parts communicate with each other using this AXI interface, which is a very high-speed communication network between these 2 parts. So first, what we do is after finalizing the network, we train it and transfer the weights, training weights to the FPGA memory. And then we create the same logic of the network on by using high-level synthesis on a tool called Vivado HLS. And after synthesizing the logic, we reprogram the FPGA hardware. And after that, we goes towards the application program. For example, in case of IoT devices, we capture the signal from audio. And after performing this audio features extraction, we can perform the inference on this processing system part. And we get the inference results. For example, in this case, we have speech commands classification, and we get the probabilities. And this device has another feature that multiple devices can be connected together using Firefly cable connections and can be used as a single cluster, which we are considering to use in our future work. So next, I will introduce the accelerator, which we have implemented. So in a basic convolution, we have 6 loops, which we have to compute for computing one convolution layer in the network. For example, 2 loops are for the kernel operation for each channel in the input. And one third loop is for the number of input channels. And on the output side, we'll have 1 loop for the horizontal elements of the channel, 1 for the number of channels, and 1 for the vertical elements in the output channel. So what we do is we first unroll the whole input computations into one long vector, and then we multiply this input values with the trained weights, and it gives us one output value corresponding to one output channel. So before it was going through three loops, and now we can only use one loop and simply perform the multiplication process on this long vector. And the second step is the parallelization through pipelining. For example, there are these 3 elements in the output channel. There are 3 output channels, and corresponding to each, we have one computation like this. So if we do the computation one by one, it would take us 3 times the time which will take for one computation. Let's consider X number of cycles, and the total number of cycles would be 3x. But because these operations are independent, because input values and the weights are independent, so we can perform these operations in parallel, and all of these operations can take place in X number of cycles and plus 2 cycles for scheduling. And this is how the pipelining works. And basically, this is the pseudocode, and in HLS, Vivado HLS, we make the logic in C language, and there are some functionalities like pragma functions, which we can use for unrolling and pipelining the loops. So the question is, why not unrolling the whole convolution step by using these pragma operations? Technically, we can do that, but as we increase parallel operations, the hardware resource utilization will increase as well. So in practical scenario, an optimal balance between parallelization and resource utilization has to be found for given logic. For example, in this case, we unroll inner 3 loops as shown in this figure, and we parallelize the 1 loop above that. So this is the maximum parallelization and loop unrolling which we could do for the given device, depending upon the available resources. Next is our experimental results. So acceleration results in terms of end-to-end latency for inference were measured. And by end-to-end, I mean by giving the input features matrix to the device and getting the output probabilities. So the latency is average for 10 inference experiments. So here are the results. So this blue is the base model implementation, and we see for this CaseNet 1 lighter version of our network. The standard implementation without any optimization takes 0.61 seconds, and for the CaseNet 2, it takes 0.33 seconds. There are some other approaches, acceleration approaches for CNN, which were proposed in the literature, and they have achieved these acceleration factors. For example, Alamo could accelerate by 1.9, followed by 2.14 and 6. But in our case, the best acceleration which we could achieve was 6.77, which is the best among all of these references. But for the CaseNet 2, the acceleration factor is a bit lower. And the reason for that is as follows. We had some observations. 3 convolution layers network achieves larger acceleration factor. The reason for that is larger convolution layers means more concurrent operations in convolution, which means there is more opportunity for parallelization. So in case of this network, we had 3 convolution layers, which means we could do more parallel operations, but in case of 2, we had less opportunity for parallelization. So finally, to conclude, we have proposed a CaseNet network, which is lightest CNN network to achieve state-of-the-art accuracy for speech classification. We have demonstrated data-centric approach to improve the performance of audio classification tasks. And we have implemented Accelerator for FPGA for speech classification. For future work, we are planning to extend audio classification, which is only for one short signal, to full automatic speech recognition. And also the final goal is the integration with IoT devices for developing an end-to-end sound source localization, separation, and speech recognition framework in edge computing. That's the end of my presentation. Thank you very much for your attention. And if you have any questions, I'm happy to answer that.